Good morning, Dr. T.
Good morning. How are you doing,
I'm
Fook?
doing fine. How about you, sir?
Good. I'm doing all right. I'm really happy to see everybody here, and I'm happy that you said something because I was just lost in the Zoom menus, trying to figure out how to make my picture a little bit bigger.
Nice.
It's sort of in the corner,
I see. Yes,
but I can't figure it out. Yeah,
yes, sir.
I I occasionally watch my own videos. You
Yes,
know, and it's not because I'm vain, but I like to see a bigger picture of myself. Oh God, let's see here. Uh, okay, floating controls, good. Chat display of the. Okay, alrighty. So I'm gonna go more. Let me go chat to see our chat. Okay. Okay. So I may even try to put us into a breakout room today, just because I think it's possible, not because I am in any way an inspiring instructor. As a matter of fact, I think I'm the most one of the most dispiriting instructors you guys will take. And it has to do with my laziness. I'm just so damn lazy. Let's see here. Um, so let's go ahead and do some. Let's do a little homework first. You guys want to do that?
Yes, please.
All right. Excellent. Excellent. All right. So I'll do 6 problems, and then I'll take some questions, and then with the 10 seconds we have left, I'll do 20 slides on I'll do 20 slides on uh, PowerPoint,
Katie, can you please
So
read the last two questions? 44, 40, 43, 44 or something?
okay, the last 2 questions.
Yeah, please.
Sure, I will get to them. Yeah. I would do them right now, but they're probably too hard, so I have to do them Thursday. Because I know you wouldn't ask me an easy problem. So I'll make a note here to do the last 2 problems. And um, I've also got a bunch more that I need to do, which are FTIR problems. So I'm going to start out with some UV Viz problems, and again, apologies. I didn't think these were going to quite be. I mean, some of them are fairly straightforward, but some of them are a little bit more tricky. I'm just going to go over them, and so please enjoy the ride for a moment. Van, am I going to see you today, or do you have lab today or next week? Oh, you're muted. Sorry, hon.
Oh, sorry. I have lab tomorrow.
Okay, great. I'll see you tomorrow then.
Yeah, thank you.
Cool. Of course. Okay, so let us. Let's see. Now I've got to actually get the questions for myself. Um, So I'm going to go to a new share. And so our first problem is to compute the dispersion. Of a grating. And the dispersion is the delta phi over delta lambda. This is the change in angle. It's diffracted angle, really, with respect to the wavelength of light. So you may think of this question as answering, how big is your rainbow? You know, because the larger delta phi, it means it's more spread out. You know, but so in order to do this one, we have to look at the question of delta phi delta lambda, and that is simply equal to n over d cosine phi. And in this case, if you have a grating, then there is an angle with respect to the normal of theta, which is this one, and a new angle phi. And in general, theta is not equal to phi. You know, it's because it's not really straight reflection. It's more, it's actually diffraction. So in any case, you can, the key to this one is to understand, interpret the question. Where D is equal to something about 1,500 lines per centimeter, right? Right. But D actually has the units of distance. And if you put in for D, 1 centimeter over 1,500, this is actually numerically what D is equal to, then you'll get the right answer, you know. And you have to, so this is, you know, this will give you the actual D value. And then there's another trick in this one, which is to use, so like, if you plug it in that value and then you get delta phi delta lambda is equal to 1 over, whatever this 1 over 1500 times, say, cosine of 15 degrees or whatever. Then what this comes out to is, it'll come out to, say, 1553 radians per centimeter. And this is the key, is understanding the natural unit that this comes out with. So what you want to do is convert radians per centimeter to degrees per micron. So you take the answer here in radians per centimeter and you multiply that by 180 degrees over pi radians, and you multiply that then by I don't know, 10 to the minus 2 centimeters, 10 to the minus 6, I'm sorry, 10 to the plus 2 centimeters over 10 to the plus 6 microns. And then that will cancel the centimeters. And then this will give you the proper answer. It comes out to 8.9 in my case, degrees per micron. Okie dokie. So I know I'm moving quick, but I promised to publish this recording. So let's see here. So the next question is, what grading spacing what should a grading spacing be for a given experiment? And you can't always determine things, obviously, but if you have theta is equal to 49 degrees and phi is equal to minus 31 degrees, right? That's a little, this is a little twist here, that your theta value will actually be negative. And you're wanting to image light of 550 nanometers. And you're going to do it in first order. Then what value of D, what grading constant D is optimal? And you simply use the grading equation, which is n lambda is equal to D sine theta plus sine phi. And you rearrange for D. D is equal to n lambda over sine theta plus sine phi. And then just plug in all the values, 1 times 550 over, all these other things. And this gives you a value of 2.29 times 10 to the minus 6 centimeters. I'm sorry, meters. This is meters, right? Because if I use meters in this unit, then meters will come out in this unit here. So 2.29 times 10 to the minus 6 meters. And then what you want to do this is convert this into lines per centimeter. So first convert it into centimeters and then take the reciprocal. So we could say times 100 centimeters per meter. And that'll be, make it 2.29 times 10 to the minus 4. And then take the reciprocal of it, and then that will give you 43.58 lines per centimeter. Check. Okay. How we doing? Are we dying yet? Do you want to try something else? Let's see here. I was thinking about making breakout rooms just for the hell of it. But I don't really have a problem for you. So that won't work. Well, I need to have a problem and then we make a breakout room. Then you kind of privately work on the problems. That type of thing. Okay, I'll remember that for next time. Okie doke. So, so the next question here that I want to do for you is one about grading resolution. Okay, so, and what this says is that lambda over delta lambda is equal to little n times big N, right? Oh, who's the kid? Who's the little boy? Hello. Hello, buddy.
Hi.
Hi, how are you, sweetheart?
Good.
You good? It's early, huh? Are you going back to school or not yet?
I'm still in school.
Cool. Excellent. Excellent. I love it. I love it. Buddy. Okay. So let's see here. I am going to keep going here. So, and what this means, what this formula means here is that this is the number of blazes that you illuminate. Basically, this is the size of the grating, you know? Number of blazes illuminated. So if you have a grating and it has, you know, if you just have two blazes illuminated, you really can't separate light. But if you have thousands and thousands of blazes simultaneously illuminated, then you can separate them. So that is big N is the number illuminated. Little n is the order, right? And that keeps coming back. And it's funny because this also suggests that in higher order, you can get higher resolution, and that's true. Although there's always a problem called order overlap. So if you want to work in order 2, then you have to deal with half the wavelength light showing up at the same angle. So if you have a long wave filter or a long pass filter, then you can do that because you'll cut out the shorter wavelengths. Okie doke. So and the grading resolution problem is what resolution or how many grooves per millimeter are needed to achieve lambda over delta lambda equal to sufficient to resolve 589.59 and 589.61 nanometers. So these are the sodium D-line doublet. So there's hyperfine structure in the sodium emission that shows up. I think it's hyperfine. I'm actually a little bit out of my wheelhouse, but it's higher resolution structure in the sodium emission, and I recognize these two numbers. So so if you need to resolve them, you need a high resolution monochromator. And so what you would do is that you can say, well, delta lambda here is equal to lambda over n, right? You just rearrange that equation. And that's equal to lambda over r. Right? And so that's going to be 560.37. This is the average lambda. It's not important that you use that. And then this is, I don't know, 1.1 times 10 to the fourth. So this is one way to do this. I see also that this is the second of two problems. So, and I'll let you do the first one yourself. It's trivial. Okay. So I'm sorry I'm racing here. It's only 7:50, so we're doing okay, actually. Okay. So now let's do here's a question on calculating the D value for a grading given delta lambda over lambda, I'm sorry, delta phi over, delta phi over delta lambda is equal to 5.80 degrees per nanometer, or per micron, This is micrometer. So okay, and another piece of information we have is that phi is 9 degrees and n is 1. That's first order. Right. So delta phi over delta lambda is equal to n over d cos phi. So d is equal to n over delta phi delta lambda times cos of phi. So that will equal 1, the number 1, over okay. Now we're going to put in the 5.80 here. This is degrees per micron, right? And then we're going to multiply that by pi radians per 180 degrees. And then we're going to multiply by the cosine of 9 degrees. Okay, and that gives us a d value equal to 10.0 microns. There's the answer. So that means that for all the specifications that they made above, we would need a grading with a spacing of 10 microns. Okie dokie. So the next one is the hardest one. So I'll go ahead and give it a little bit of time. And so here we go. In the question, this is a stray light question. And has to do with absorbance spectroscopy, right? And it's a little bit hard to pick through the information that they give on this problem, but one of the things they do say is that stray light is equal to 0.4%. Okay, so what I'm gonna so that we can basically go to an apparent absorbance. I'm sorry. Let's start with apparent transmittance. T sub A for apparent, and that is going to equal P over P0, right? Plus PS and plus PS in the numerator and the denominator, right? So P sub S here, this is going to be 0.4% of P0. And so we're going to let P0 equal 1. And we'll do all the other problems accordingly. So in this case, PS is equal to 0.4% of 1, which is equal to 0.004 units of light power, right? So so now the next question is, or the next information they give us is that true transmittance is equal to 0.0613. I'm not really sure when you would have this information, like the stray light and the true transmittance, but in any case, they're going to ask us to compute the apparent transmittance. Right? So the apparent transmittance here will equal 0.0613 plus 0.004 over 1 plus 0.004, right? And this will equal 0.0650, right? So the true absorbance will equal the negative log of the true transmittance, and that will equal the negative log of 0.0613, which will equal 1.213, right? 3 sig figs here, 3 sig figs here, right? And A sub A will equal the negative log of T sub A, which will equal the negative log of 0.0650, which will equal 1.187, right? Again, 3 and 3 there. Now, this is the apparent is less than the true. Right, that's one of the truisms here. That this means that the apparent absorbance has a negative deviation from Beer's law. Okay. So the next one is pretty darn tricky, right? And they ask you to calculate the stray light if the apparent absorbance is equal to 1.995 and the true transmittance is equal to 0.0100, right? So this is kind of where we can start, right? So if T sub T is 0.01, then P sub T is equal to 0.01. And so all we need to do is set up the equation that 0.0100 plus P stray over 1.0000 plus P stray is equal to the negative or the negative exponentiation of this value, 10 to the minus 1.995, right? This is T apparent, or yeah, this is T apparent. And so by doing this, so this comes out to a number which is 0.0101116, right? And then you can solve this for P sub S is equal to 0.00
Dr. Terrell, can you
0117. Sorry, yep. 0.000117, right? And then, so this is 0.01%, Alrighty. So this is a little bit difficult. It's like multi-steps, and I don't like it that much, but and I won't require this level of detail on the final exam. So, all right. So last but not least here, we have got a rather tricky stray light problem. And the stray light problem starts out by saying that you can have a maximum error in absorbance equal to 7.200 times 10 to the minus 5. So that's a pretty small absorbance error, right? So I'm gonna say also here that well, let's take a look at it, right? And this is going to happen at an absorbance equal to 1.4. And then since it's 10 to the minus 5, it's like 1, 2, 3, 4, 5, 6, right? So this is 10 to the minus 5 absorbance units, right? And then there's actually 2 zeros after that. So, you know, it's kind of crazy to end up with that accurate of an error value, a maximum error value, right? But we can go with it for now, right? So what that means is that if we plot absorbance versus wavelength here, I'm sorry, not wavelength, absorbance versus concentration here. And 0.5, 1, 1.5, right? Normally what we would expect is for there to be a straight line relating these two quantities, right? And what we've calculated is that there's going to be an error, or what we're stipulating is the maximum error of 7.2 times 10 to the minus 5. So let's just say that at 1.4, right out here, that there's going to be some negative error, right? And the magnitude of that negative error here is equal to, say, minus 7.2 times 10 to the minus 5, right? So so they're basically asking, what is the maximum, what stray light component corresponds to this amount of error? Right? And so the way to solve this is first we'll look at the true transmittance. And this is going to be 10 to the minus 1.4, you know, all those zeros, right? And so this will equal P over P naught, which will equal 0.0398107 over 1.00 right? So this is the true transmittance, right? This is P true, this is P not true, right? And then what we're going to say is that if we look at the apparent transmittance, right, which should be 0.0398107 plus some stray light component over 1.000000 plus the same PS value, we're going to say that this value here okay. I see. We're going to say that this value here will equal T apparent, right? So this, and T apparent is 10 to the minus 1.4000 minus 7.2 times 10 to the minus 5, right? That's a big step right there. This is T sub A, which is equal to T sub true. I'm sorry, it's equal to A sub true. This is the numerator is equal to A sub true minus A sub apparent. No. The numerator is equal to A sub apparent. This guy up here, this is A true, and this is the delta A, right? So A apparent is equal to A true minus delta A, because it's a negative deviation, right? And so this whole thing here is equal to T sub apparent, right? And that's T sub apparent there, right? So that's equal to T true plus the PS component in the numerator and the denominator, right? I'm sorry, this is a bit of a cluster problem here. 398173. So the difference is in this digit, these three digits here. Right, so this is 0.0398107 plus PS over 1 plus PS is equal to 0.0398173. So that's the difference we're trying to make up for by adding P sub S there, right? And then when you solve for PS, you get a value of 0.000006892, right? Which is 6.86 times 10 to the minus 3%. Oh my effing God. All the effort to get to a tiny value, which tells you the maximum stray light or the amount of stray light that will give you a certain deviation. Okay. All right. So if there's any other homework problems, I think I'm already scheduled for Friday to do 35 and 36. Let me know. Maybe let me know in the chat or something. So I'm gonna share. Whoop. PowerPoint again here. Okay. So where we were last time is we were chatting about filters, right? And I just talked about the existence of both long and short pass filters. Whoops. And the thing I'd like to draw your attention to now is let's just take one example of a long and a short pass filter and see if you can see where it might fit. So if you have a holographic filter, this is called a holographic notch filter. There is an inverse type of filter called a band pass filter, right? So let me switch over quickly to the document cam to frame this question. If you're looking at the transmittance, transmitted power versus wavelength here, and you can have maximum of 100 and minimum of 0. And you can have one type of filter which essentially does this, right? And this is called a notch filter. And you can also have a bandpass filter which does the opposite, right? And my question for you guys is, which one is for use in Raman spectroscopy, and why? So who can approach this question? Who can answer this question? Now that I've bored the crap out of everybody. Okay, this might be a point where we have to have a breakout room.
Wait,
Oh
Dr.
my
Taro,
God.
what does the question say? Could you just read it real quick?
Which one is for use in Raman spectroscopy and why? Which is it, the notch filter or the bandpass filter? Which one of those is
So in Raman,
Mhm.
so in Raman, you're capturing the scatter, right?
Yes.
Like you're
Yes, you
capturing the
are.
photons that scatter back.
Yes, exactly
Um,
right. Exactly right.
So if you're catching the scattering photons, you'd probably want the bandpass filter.
That makes perfect sense. That makes perfect sense.
But it's wrong.
And so I would like to know. So let me ask you this instead, Kareem: is Raman elastic or inelastic scattering? I know I added an ambiguous or maybe a difficult word in there, and I kind of do that intentionally, right?
Yeah, I think it's
So
inelastic.
exactly right. And what does inelastic mean?
We can open the floor up to other people, maybe. I don't know if anyone else knows.
All right, who can answer what inelastic means? So if you're talking about, say, a rubber band, and you stretch it, you do work on the rubber band,
Not flexible.
then we run it. Sorry?
I think inelastic meaning
They,
not flexible.
someone has Google. So inelastic in this case means that the energy that you put in, like stretching a rubber band, does not all come back. So elastic means that you put energy stretching and you get all the energy back when you relax, right? But inelastic means that you don't get all the energy back.
Is it because it's
And in this
losing energy
case,
through heat?
exactly right, exactly right,
Oh,
exactly
okay.
right. Exactly right. Yeah. So, recall that in Raman, there's two processes, right? One is Rayleigh and one is Raman. Rayleigh scattering is elastic and it's dominant. And Raman scattering is inelastic and it's very weak. Right? So, if you want to catch the very weak inelastic photons, which of these filters do you need? A bandpass or a notch? Let's say that
Oh, I think a notch, because you're trying to exclude that middle section, right?
I give you full points, Kareem.
Thank
I'm
you. I
very
got it.
proud of you.
I got the guess on the second try, and there are only two options.
Excellent, 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 excellent. I like it. I like it. But your rationale was correct, right? The rationale is that you want to collect the photons that are not at the laser wavelength, right? So, for example, if you have we actually had an unfiltered Raman system when I was actually an undergraduate. They used the helium neon laser, and they went and and they just scanned that mother, and it and then it registered a peak, registered a peak, and then it went wang, and it went because it was off scale, and then it came back down, and then and because this is the Rayleigh peak, and you can't always see these side bands. If the Rayleigh peak you can't always see them in the presence of the Rayleigh peak. So, any case, good job. And now let's move on to detectors. And I'm going to give you guys a whirlwind tour of a couple types of detectors here. So, detectors, right? So it's just, this element right here. This is the detector. And you ideally will be sensitive over a wide wavelength range. It'll be low background. It'll be low noise. These are basically the characteristics you want in any detector, right? So let us then see what types of detectors are available, right? And these are the transducer type, right? The transducer type can be a semiconductor like gallium nitride, which sees only in the ultraviolet, or it can be indium gallium arsenide, which sees in the near infrared, or it can be silicon, or it can be any other variety of materials, each of which is designed to liberate charge when a photon hits it, right? Now, in the old school, right, liberating charge meant literally emitting an electron into vacuum, right? So, and this is still the single most sensitive way to detect photons. And this is called a photomultiplier tube. And in a photomultiplier tube, let's see, let me make this a little bit bigger here. All right, let's go to 200 here. Sorry, there we go. In a photomultiplier tube, you have a cathode here. Oops, the fuck? Why do they have a grill and a cathode? Okie dokie, well, I think that this is mistaken, but anyway, you have a photocathode here, and the photocathode is actually biased, right? So the photocathode has a large negative voltage applied to it. And yes, I will do number 44 on Thursday. And so what happens is that when a photon strikes this photocathode, it can cause the emission of electrons into vacuum. right? And that requires two things, really. It requires sufficient energy for the photon and sufficiently low work function for the metal. So we already know what work function is because we're chemists. And the lowest work function metal is, excuse me. Oh, sorry. I'll try to mute myself next time. But the lowest work function metal might be lithium, for example. And so, and that is just very correlated to the electropositivity or the lack of electronegativity in the metal. Chemists define it as the amount of energy that it takes to get the electron out of the metal and onto some other species like H+, right? That's the electrochemical potential. A physicist describes it as the energy that it takes to get the electron off the metal and into vacuum, field-free vacuum. So there's a little bit difference in the way that we do that, but in general, you need a low work function metal and you need a high enough energy photon, and you can also effectively reduce the work function of the metal by applying a negative bias to this photocathode here, right? So when the electron is emitted from this negatively biased photocathode here, it is accelerated towards what is referred to as a dynode. And this dynode may be held at, an additional like 40 or 50 volts, higher potential. So that means that this electron is going to accelerate like crazy through the vacuum. It's going to hit this with like 40 volts. And then that's going to emit like 10 electrons. And then that's going to emit 10, 10, 10, 10. And by the time you're done, you have this little anode here. And the anode should be picking up at least 1 million photons for every, or electrons for every photon that was absorbed. Excuse me. So that's how a photomultiplier tube works. And the photomultiplier tube is still the single most sensitive single photon detector, right? So if you go to the ice cube in Antarctica, that's a cubic kilometer array filled with a bazillion photomultiplier tubes. And these are all monitored simultaneously. Every one of them has like a freaking atomic clock, right? And every time one of them records a pulse, they literally get a trajectory for a particle going through that thing. And that's designed to pick up cosmic rays, i.e. neutrinos from space. So that's pretty wild, huh? But they still use PMTs there because they're so sensitive, right? Now, oops, let's, obviously in mammals and other critters, mostly animals, right? Since an animal, if it sees something coming, it can do something about it. But a plant, they just close their eyes because there's nothing they can do if they see a hatchet coming their way, right? But animals use a type of photomultiplier system, right? Which relies on the isomerization of rhodopsin from from cis to trans, right? And I don't really know how this how to drive a conformational change with the energy from light, but I suspect what it does is it mainly lowers the barrier. So it probably produces an excitation that's somewhat centered here, and that reduces the electron density in the bonding orbitals. So it allows more freedom of rotation of this bond. But and then it just rotates thermally. But when it absorbs light, then it creates an electrochemical signal along this membrane, and then everything goes crazy from there, right? But so back in the world of technology, a very important type of semiconductor, or a type of detector, is a semiconductor. And for semiconductors, what happens is that the semiconductor absorbs light and it liberates a type of carrier within the semiconductor, referred to as an electron hole pair. And so I think the best way to think of a semiconductor is thinking of intrinsic, say, silicon, right? Now, silicon is silicon has a diamond structure, which means that the atoms in silicon are arranged tetrahedrally relative to one another. And because each silicon has 4 valence electrons, you can make a perfect crystal of silicon. And that perfect crystal will essentially insulate electric charge because there are no free electrons in it. However, when you, oops, I'll be right back. There you are. However, when you absorb light, or when silicon absorbs light, what happens is that an electron from the network of bonding electrons is promoted into a similar network of antibonding orbitals. And the antibonding orbitals are now, well, in an antibonding orbital, the charge is free to move because there's no violation of the Pauli principle when that electron changes place. In a filled system, such as the intrinsic silicon, the electron cannot change places because changing places will cause the electron to violate the Pauli principle. Okay, so somebody tell me what I just told you. Somebody paraphrase me and tell me back.
You can excite electrons to antibonding orbitals because you don't violate the Pauli exclusion principle. And so that makes these valuable semiconductors.
Excellent, excellent. That was a slight mixture of kind of 2 concepts. One is that you can excite the bonding orbitals into the antibonding orbitals, right? And 2 is that when you do that, the bonding orbitals, or the electron in the antibonding orbital can move.
Are they moving up
because
to
by
another
moving
antibonding orbital? Oh, sorry, no, go ahead.
No, that's a good point. That's a very good question. So I'm going to have to approach this with no diagrams here, right? Because the diagrams can be deceptive. And I always think of electrons literally moving up as though they were going fucking up in some gravitational field or something. But really what happens is that the electron simply acquires more energy. The electron becomes more energetic, and in so doing, it also occupies a new state. And electrons in this new state, this new antibonding state, they can literally physically move in X, Y, and Z because there are empty antibonding states everywhere. However, before the electron is excited, it can't move because there are no bonding states that are unoccupied. Was that clear as mud?
So it's starting off in the bonding state, is what you're saying, right?
Right.
Oh,
Exactly
okay.
right. Exactly right. Yeah. So if you're a piece of silicon, you're just pure silicon. It's called intrinsic silicon. Can you conduct electricity?
No.
You cannot. Exactly right. Intrinsic silicon is an insulator. And why not? Why can intrinsic silicon not move charge?
Because those electrons are trapped in the bonding state, so they're not moving between orbitals.
Yeah, that's essentially true. Now, when it's almost as though if you're an electron in silicon, you say, "Wow, I feel an electric field. I'd like to go see my neighbor, right? I'd like to tell my neighbor about this electric field that I can feel, right?" And then you say, "Okay, I'm getting ready to hop. I'm gonna hop over to see my neighbor." But when you get ready to jump, you say, "Requesting permission for landing on my neighboring silicon atom," and your neighboring silicon atom says, "Go to hell. You can't land here because I already have a full valence. All of my electrons states, all of my electronic states are occupied." Does that make sense?
Yes.
Excellent. Excellent. So in order to hop over, first you have to hop up. You have to gain a bunch of energy from a photon, and then suddenly you can go anywhere you want, because any direction you look, all you see are vacant orbitals. Well, almost any direction, right? And so from that point, you are actually a highly mobile entity, and you're called an electron in the conduction band. The conduction band is an antibonding orbital network in the silicon. Does that make sense?
So does that ultimately translate over to like voltage that you're putting through the silicon? Is that what determines the energy?
No, the energy of the state is determined by the charge on the silicon atoms. You know, it's how hydrogen makes one bond, helium doesn't make any, and lithium makes one, beryllium makes two, boron makes three, carbon makes four, da da da. That sequence,
Yeah.
Well, silicon is at a atomic number where it can make four bonds, right? It has a neon core, I think, and then it has enough, and then it has 4 more electrons, right? And so it can make 4 bonds.
So there are like modifications that happen to the atom itself.
No, that's actually not true. There are tiny distortions. There are tiny distortions in the crystal lattice, and they go along with this thing called a polariton, which is the polarization of the crystal when you have an excited electron hole pair. But to 99th percentage, there's no distortion to the crystal lattice due to the excitation of a single carrier. Did that help, or did that muddy the water?
Yeah, no, I think that makes sense. Thank you.
So let me close then with another question for you guys. If you are silicon and you have an electric field across you, you're pure silicon, you have an electric field across you. Is there an electric current? Yes or no? Is there a constant flow of electric current? Nicola?
On just silicon?
I think so.
Right,
No.
right.
No.
No, exactly right. There's no flow of charge, right? Because the electrons, when they try to move at that same energy, they can't move, right? Now take that same piece of silicon and shine a photon into it. And when that photon is absorbed by a silicon atom, it promotes one of the valence electrons into the conduction band. Now, the electric field is still there, and what will happen to that charge? Will that charge recombine? Or will that charge be swept apart by the electric field?
Swept apart.
Exactly right. Because God wanted us to see. Damn it. Okay, my dear ones. That is all for today. And I will do question 35, 36, and 44 on Thursday. All righty.
Okay, thank you, Dr. T.
Thank
Thanks,
you
Dr.
so
Turo.
much for your attention. Thank you. Thank you.
Thank you, Professor.
Excellent day. Thank you.
Doctor,
Yes,
may I
Fook.
ask you quick questions?
Okay. Are they related to class,
Yes.
or are these other things related to graduate
No,
school?
it's last. This last.
Okay.
I'm still thinking like on yeah. So for homework, is it possible if you extend the due dates for a bit? Because it's kind of 44 questions. I have my PChem like homework, and it's tons of work, and I'm sure others would be greatly appreciative if you extend it a little bit, Dr. T. For
Okay. I'll think about it.
yeah,
I'll probably extend it to Monday night.
or something along those lines. Yeah.
Yeah, Monday night. Okay, I'll do it.